We've all been there before. You're out of time, you're out of board space, your bomb is maxed out, and there's a problem. Your ESD protection just isn't up to snuff. One big old spark or arc and it's lights out for your design. If only you had some kind of insurance to help you out. You know, swoop in like that duck from television and poof, no more ESD issues. And hopefully none of those lightning strikes again. Yep, we're talking about circuit protection. And it ain't pretty, my friends. Hi, I'm Amelia Dalton, host of Chalk Talk. You don't want to find out the hard way. Again, right? ESD, lightning, you know what I'm talking about. Today, Wayne Dossey from Bourns and I are talking about port protection, industrial communications, harsh electrical environments, and RS-485. Looks like there's a storm brewing in yonder hills. We better get a move on. And before we get started, don't forget to click that link. There you can find out even more information about RS-485 port protection solutions from Bourns. Hi, Wayne. Thank you so much for joining me today.
Oh, hi, Amelia. So glad to be here.
Okay, Wayne, we're here to talk about RS-485. Now, I don't know about you, but when a storm comes through or a power outage, I'm having all sorts of ESD problems. I've burned up some sensors. Can you help me with my RS-485 problems?
Oh, sure, Amelia. I can do that. You see, Bourns has many circuit protection devices, and by developing new ones, they keep getting smaller with new capabilities. Bourns provides circuit protection devices for every area in industrial settings. Many are applicable to transportation applications and other areas outside the manufacturing plant. In this discussion, we will specifically consider protection against threats to RS-485 communication systems. That is the industry standard specified in TIA EIA 485.
Okay, so Wayne, before we get in too deep, give me a brief explanation on what RS-485 is all about.
Let's talk about that for a minute. The RS-485 Industrial Communication Standard is published by the Telecommunications Industry Association. The standard allows for up to 256 receivers connected to one line. This depends on the line loading, receiver impedance, and line length. The driver ICs capable of 200 milliamps will communicate to about 4,000 feet at 100 kilobits per second. On short lines, several megabit per second rates are attainable. For RS-485, a two-conductor balanced cable supports differential voltage pulses that represent ones and zeros, the binary states. A ground connection is required, usually connected as a shield over the twisted pair wire with one or two pairs in the cable.
Okay, Wayne, you mentioned differential. Now, what exactly is that?
Well, this diagram shows the voltages on the pair of wires. Balanced, twisted pairs naturally resist external voltage and current surges since each wire receives the same interference. In differential signals, one side goes positive and the other goes negative with at least 200 millivolts of difference for signal detection. The shortest time between voltage changes is the bit period equals the baud rate up to 35 megabits on short lines. Receivers reject common mode voltages within the maximum range of -7 to +12 volts. In this diagram, on the left-hand side, shows the maximum voltage the signals can be, -7 volts up to +12. On the right-hand side, there are three examples of the smallest voltages that can be on the lines, with a 200 millivolt difference between the voltages on the two wires.
Okay, Wayne, these waveforms look fine to me, but I'm guessing reality is a bit different. What is there to protect from data errors?
Oh yes, RS-485 is also vulnerable to data errors. RS-485 is also used for outside buildings where big ugly things happen. Here's the reality. RS-485 is used for exposed and remote areas. It is subject to miswire, power cross, and lightning effects. Communication devices can be pole mounted, up on a kiosk, a rooftop, for example, security cameras. The wires experience power frequency inductive interference, harsh electrical environments, industrial plants with motors, actuators, electrical arcing, and electrical substations.
All right, let's get into some details, Wayne. How can I protect my designs from all of these big bad threats?
Here are some examples of RS-485 circuit protection components. Some previous and presently used methods are shown here. You can use TVS diodes for ESD protection. You can use passive RLC components, as in normal filter elements, and make a low-pass filter. Also, you can use diodes that clamp the voltages to the supply rails. The problem with these is that the protection is tied to specific common mode voltage ranges. These shunt components provide only modest protection. These methods are customized to the length of line and interference conditions. Many components have limited surge withstand capabilities. Components with sufficient surge current capability use much real estate.
Okay, Wayne, so what's Bourns' take on all this?
Well, let me show you a better way. This is what RS-485 circuit protection using the solution that Bourns provides looks like. Specific components will provide coordinated transient protection. This solution uses a few robust and proven components. These protection components are designed to suppress specific transients. TBU series blocking is the cornerstone of Bourns' RS-485 solution. For limited exposure applications, the TVS alone may be sufficient to protect the interface IC. Environments with large and fast surges require the multi-stage solution with TVS, TBUs, and GDTs. This solution provides rugged coordinated protection against lightning, excess current, and ESD.
Okay, so on the previous slide, Wayne, I only see part of the receiver. What about the transmitter?
Well, the RS-485 integrated circuit usually contains both receiver and driver. The line driver is protected in the same way. The line driver outputs the signals to receivers through the same protection components. The TVS diode adds less than 100 picofarads capacitance, and GDTs 1 to 2 picofarads more.
Okay, Wayne, but what if I don't really need all of that resistance in my circuit?
Well, the TBU adds a few ohms that can be combined into the impedance termination.
Okay, cool. Oh, so I have 4 parts to protect my line driver, but how does that actually work?
Well, the TVS suppresses the very fast ESD and EFT pulses and prevents damage to the driver receiver IC, the absolute guarantee to avoid excess voltage on the IC. The TBU transient blocking unit detects excessive current and blocks it from reaching the TVS. The GDT, a gas discharge tube, protects the TBU from excessive voltage such as those found in high-energy lightning surges. An MOV can be used in place of the GDT for applications with limited lightning exposure.
Okay, so what is a TBU? I'm not sure I've heard of that term before.
Well, the TBU is a transient blocking unit. In normal operation, it appears as a few ohms in series depending on the voltage and current ratings. The TBU responds to a high current by blocking current surges as a series circuit element. The TBU is bidirectional and operates in a manner similar to a switch. After blocking the surge, the TBU resets itself after the overvoltage condition dissipates. The TBU is based on MOSFET technology.
Okay, so can you show me a visualization of what we're talking about here?
Sure, there's one in this slide. In this diagram, we will follow the operation of the TBU as it detects an overcurrent event. A voltage surge comes into the circuit where the TBU is waiting at point 1. The voltage surge increases the load current to the point where TBU triggers at point 2. The TBU transitions from a low impedance to a high impedance at point 3 in less than 1 microsecond. The load voltage after tripping the TBU 0.4 is controlled by the load line between the TBU and the TVS. The TBU stays in the high impedance condition until the overvoltage condition dissipates. The primary overvoltage protector, the GDT, and secondary OVP, the TVS, devices are coordinated by the TBU series impedance. Coordination typically requires a secondary OVP, the TVS, to limit the voltage at the load, and a series element, the TBU, that rapidly builds a large voltage to activate the primary OVP, the GDT. During the surge, the TBU changes from low impedance to high impedance. When the TBU changes to high impedance, the primary OVP will activate and shunt the excess current in the transient to ground.
Okay, Wayne, I'm guessing you guys have some solutions in this space, or you wouldn't be here with me today.
Yes, let me show you the Bourns protector options. For the primary OVP, Bourns has these options. Select the option that fits the maximum excess current with a protection voltage to keep the TBU safe, like listed here. Different voltage GDTs work with different TBUs. The MOV can be used in place of a GDT for limited surge exposures. You can match the components to the application. You select the TBU series element with the voltage rating that is safe with the primary protector and the current rating to protect the secondary protector. If you're using a high current driver, be sure to use a TBU with sufficiently high trip current. TBU components have several options for different types of systems and thread environments. Any recommendation of specific components is application specific.
Okay, Wayne, that's 2 components, but what about the second protector?
Well, the secondary protector also has options. The intended protector for the maximum RS-485 voltage levels at plus 12 and minus 7 volt common mode range is the CD-SOT23-SM712. For a system designed with 0 to 5 volt range, use a lower voltage protector device, the CD-SOT23-0502U.
Okay, Wayne, you've given us a lot of options, and now I have a handful of components, but how do I put this all together and start testing?
Well, to make it easy for you to test with different selections for the protection components, Bourns has an evaluation PC board with soldering pads and holes for several different sizes of components. Here's what's on the board. J1 connects to the line input. There are spaces for MOVs, GDT, a TISP, TBU, and TVS. J2 connects to the receiver driver integrated circuit. Now here's the practical side of using the RS-485 demo board. The demo board RS-485 eval board 3 can be configured in several ways. The complete solution is available with TVS, TBUs, and GDTs. Alternatives consist of adding higher voltage and current GDTs. Also add MOVs as a separate part. Other voltage protection levels can be used for different system common mode voltage designs. You select a secondary protector for the best voltage protection for the IC. Here's what's on the eval board when you receive it. There are 2 90-volt 2017 flat GDTs. There are 2 650-volt 300 milliamp TBUs and a TVS SM712. Now here's a picture of the eval board that you receive. It has room for many different configurations of the RS-485 protection circuit. It's ready to solder on and is made of FR4 PC board. You connect J1 to the line and J2 to the interface IC. These parts can be removed from the board and replaced by other selections.
Okay, Wayne, this has been quite a lot to cover today. Can you recap your main points for me?
Yes, I can. We have discussed the protection of RS-485 data transmission circuits, the solutions for protecting the transmission and reception, and the methods for removing excess voltage and current from the transmission lines. The RS-485 demo board can be ordered from Mouser, part number 652-RS-485 eval board 3. Alternate parts to test with your system can be purchased from Mouser.
Excellent. Well, I think that's all I have time for today. Thank you so much for joining me, Wayne.
Well, thank you, Amelia, for the opportunity.
And before we go, you didn't forget to click that link, did you? There you can find out even more information about RS-485 port protection solutions from Bourns. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, check out the Chalk Talk section of eejournal.com or head on over to YouTube, keyword eejournal.